Okay, we'll start. Good evening and welcome to the fourth event in our 2022 speaker series, Surprising Science, Borrowed Ideas Leading to Unimagined Consequences. I would like to acknowledge and pay respect to the traditional owners of the land on which I am this evening, the Ngunnawal people. It is upon their ancestral lands that the Academy of Science is built. As we share our knowledge, teaching, learning, and research practices, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of this country. I'm Mahananda Dasgupta, a fellow of this academy and one of the conveners of this series. Also joining me to convene this series is Professor Drew Evans from the University of South Australia. Hello, Drew.
Hi, Amanda, and thanks for the introduction. I'm really enjoying working on this particular series with you. We've heard some amazing stories so far, and just to let out a bit of a secret, there are some fascinating stories to come. Today, I'm proudly joining you from Ghana country, and I too pay my respect to elders past and present. To everybody that's joining us live or online, I'd like to thank you for joining us this evening. Tonight, we will hear about some surprising science related to batteries and soil. Dr. Chris Guppy and Dr. Mahdokht Shaibani will no doubt surprise and inspire you with their work. Now, before we get into the talks, there's just a few housekeeping things. So for those of you with your mobile phones, please do not turn them off, turn them to silent, and we'd love for you to join us in conversation on Twitter, which you can do so by using the hashtag #SurprisingScience. For those people joining online who would like to ask questions of our speakers in the Q&A session, you'll be able to do that by scanning the QR code that's on the screen. For those people who are live within the Shine Dome in Canberra, you'll be able to ask questions by moving up to the microphone during the Q&A session. And we strongly encourage you to jump up out of your seats and participate in the discussion. So now, let's hear from our first speaker, Dr. Chris Guppy. Chris is a soil chemist based at the University of New England. His main research areas are soil phosphorus chemistry, root responses to nutrients, rhizosphere chemistry, and silicon dynamics in soils. Please join me in welcoming Chris.
Thank you very much. This is my first time in the Shine Dome. I'm quite excited to be here. I've just noticed the one thing they promised me, because I have a tendency to talk and talk and talk and not stop, the one thing they promised me was a clock, and they've turned everything off. So I'm going to rely on you, Nanda, to wind me up when I get to the end. As I was introduced, I'm a soil chemist. I was just so excited by soil when I first started my agricultural science degree. I didn't think I would be excited by soil. Not many people are, that's right. Yeah, that's right. But it's just genuinely an amazing aspect of this planet. I was chatting with someone earlier and they were saying, isn't soil just a downgrade on geology? And I was very, very calm. I took a deep breath and yeah. Anyway, we're going to talk a little bit about sulfur. I am a phosphorus chemist. I do love phosphorus and I have snuck some phosphorus into the talk. But I want to just share some background information about sulfur in soil and the ways in which we have put sulfur back into our system and why we need to do that. So there's some pictures there on the slide of what plants look like when they don't have any sulfur. They look a little bit pale and seedy and not very happy, and there are reasons for that. But does anyone recognise what we're looking at here? It's a very old picture from the 1980s, and it's a picture of the destruction of forests in Europe due to acid rain. And a lot of that acid was sulfuric acid. And as a consequence of that devastation, I was only 10 or so, I think, in the 1980s. But even I remember seeing pictures of the destruction of the people are commenting on my age. Is it too high, too low? But I remember these pictures of destruction, and in consequence, Europe imposed standards on all of their coal-powered stations to remove the sulfur dioxide emissions as the coal was burnt, and they did a fantastic job, and they removed all of that sulfur from the atmosphere. So they removed the acid rain problem. But what they actually, in consequence, did was create, within 10 to 15 years, sulfur deficiency across most of the agricultural areas of Europe, because everyone was getting their sulfur for free from the power generation. And you turn off that sulfur tap, which was, well, it was a bit dangerous, but when you turn that off, things became a bit dire. And so we had to work out ways to add sulfur back into the system. If you don't have sulfur in an agricultural system, then you can see the deficiency showing up. So there's some canola. Canola's flowering at the moment. If you've driven in, it's just beautiful. Canola has an enormous sulfur requirement. There's a lot of sulfur exported in the oil. And so it's like the canary, it's yellow as well, it's like the canary in the sulfur gold mine. That's how we work out whether there actually is a problem with our sulfur status in agriculture. It's a little bit paler for cereals like wheat, and the requirements are a bit lower. But we do see deficiency in Australia due to lack of sulfur. But in the big picture, the lack of sulfur in the environment, the lack of sulfur in soils, does have consequences. This is a recent paper, I think it was in Nature, somewhere like that. But that's just showing you that as we have cleaned up power stations all over the world and taken the free sulfur out of the atmosphere, falling all over the place, you can see that the increase in fungal disease has shown up. I'm not saying this is causal, but sulfur plays a very important role in mitigating plant damage due to fungal disease. And Europe and America, lots of power plants, lots of increase in quite dangerous fungal diseases. I'm going to go back to basics because I'm not sure how excited you all are about soil. How much you know about soil. The thing that hooked me when I was an undergraduate student in my second year at University of Queensland, I was just gobsmacked that soil is actually charged, and soil is negatively charged. I had no idea. I didn't know I was at risk of electrocution just walking around on a wet day. No idea. You're actually not, just so to see. But soil is got a net negative charge, and what that means is it attracts positive cations, positive ions, and like magnets, and try and shove them together, it repels negative charged ions in soil. And so those are the types of ions that are present in soil, cations and anions. You can see I've highlighted in yellow on purpose sulfate. Sulfate is a divalent negative ion. And so it's going to be generally repelled by the soil. And if it's repelled by the soil, it's going to leach. And don't worry, I'm not going to examine you on this at the end of this lecture. This is just a picture of the sulfur cycle. And I just want to point out a couple of key things here. The first is, there's our sulfate there. All arrows point to sulfate. It's very important because sulfate is the only form in which a root can actually take up sulfur. It can't take it up as either gypsum or elemental sulfur, definitely can't take up sulfide, and the organic sulfur in a soil, the sulfur associated with carbon in soil, organic matter, it has to be eaten by microorganisms and converted to sulfate before the plant can actually access it. And so the key arrow that we're constantly fighting as agricultural scientists and soil scientists is that one there, the leaching arrow. Because our soil repels the sulfate, we need to find ways to supply plants with sulfur when every time it rains, it flushes the system of sulfur. This is where I sneak in and do a bit of phosphorus on the side. One of the first things soil scientists did when computed tomography images were used to scan humans is we immediately purloined the technology to look at what's really important in life. It's not us, it's roots, okay? And so when we grow a plant in a little column and we extract the images and look at the root system, we can see where they're growing and why. Normally we can't see that, and this was a goldmine for soil scientists. We just loved looking at it. What you're about to see here, it'll go blue. In our little column of soil, we actually placed phosphorus there. Phosphorus, even though it's also negative in soil, phosphate, it doesn't move. Romeo and Juliet love affair between soil and phosphorus. You put it in there, it doesn't move more than a few millimetres. Sulfate, it would move a few metres every time it rains. And so what plants do is they're pretty smart. They invest carbon where they encounter phosphorus. So where their roots are growing through and mother lode, they will put more and more roots in there to suck on that phosphorus because they know the phosphorus isn't going anywhere. And so when we're fertilising for phosphorus, we can place it in a band and we can let them suck on that for a little while. But we can't do that with sulfur. Our sulfur sources, we have a problem because when we put a band of sulfur into soil and we measure where the roots are, you can see there's no difference. The plants are completely oblivious to the presence of extra sulfur in the system. They just grow straight on through. And there's a reason for that. If you know that the phosphorus is going to be there for a while, it's time to put down roots and actually live there. But there's no point doing that for sulfur because it's gone the next time it rains. So you don't invest that energy, you don't invest that carbon in trying to do that. Elemental sulfur is one of the key inputs that we have been developing over, many years, many decades now as soil scientists to put into our systems. And there's a reason we use elemental sulfur and rather than sulfate. If we put sulfate in, like I said, all bets are off. We can lose it really quickly. But elemental sulfur, the plants can't take that up directly, and there are bacteria in soil that think, for reasons unknown, that elemental sulfur is the yummiest thing in the universe. And so they break that down to produce sulfuric acid. But it takes time. It's a slow release source of sulfur. And there are heaps of products on the market now that contain mixes of sulfate and elemental sulfur. So we took that idea that we've got a rapidly available Macca's type sulfur in sulfate, and we've got a source that is incredibly cheap. It just comes out of volcanoes and comes out of oil. It's a byproduct, it's a waste product. I think you can purchase sulfur in Australia for about $180 a tonne at the moment. And if you've looked at the price of nitrogen fertiliser anytime recently, it's near $1,200 to $1,400 a tonne. So sulfur's really cheap. Sulfur's really cheap. And it has the advantage in that we can change the size of the particles to change the release of the sulfur. If we make them really, really fine, they'll release a bit faster than particles that are really, really coarse. So we can put a meter in with the size of the particles. This is an experiment that he was an honours student then, but he's now a colleague, and Graham Blair is an emeritus professor and has been working on sulfur for 50 years. There's nothing he doesn't know about sulfur. But we did this experiment at Armidale. It's high rainfall, so high leaching, and we tested a range of products with the idea that if we balanced them up, we could get better plant utilisation of sulfur and not run into sulfur deficiency. I've got grazed regularly there because we did it with a lawnmower. So yeah, that's right. And these are the results. This is what we did back in 2008. This is clover yield, and the reason we use clover is because in almost all grazing systems, clover is king. It's the nitrogen, it's the protein, and it's actually the species in a pasture that has the highest requirements for sulfur and phosphorus and molybdenum. And so if you don't have enough sulfur, can I go back? Oh, previous. If you don't have it, this is a control plot here. We've seeded that with clover. There's no clover because there's no sulfur in that soil. It's a rubbish soil. But the clover responds to the sulfur. And here's a control. This is the amount of clover that we generated from a control. It had no sulfur really applied. There's a little bit of sulfur as a contaminant in ammonium phosphate. But when we added it with elemental pastilles, and these are molten globules of pure elemental sulfur, you can see that our yield actually went down because elemental pastilles of sulfur, and they're made molten because sulfur has a slightly disturbing tendency to explode if it abrades in any way, and so they transport sulfur in these molten pastilles that are basically inert, and as it turns out, they are basically inert. Nothing grew. We got this product, it was being sold at resellers. It was, the farmers weren't happy when we tested it and got that result. Here is the standard, this is the riding the sheep's back. This is superphosphate, just a basic calcium phosphate. All of the sulfur is present as sulfate. So this is what's been added to Australian farming systems for decades and decades and decades. And here's our new product where we put a little bit of jelly bean in there, a little bit of sulfate, and then we change the grading of the elemental sulfur to meter out the oxidation process. And so what do we see? We see, yep, when you put jelly beans in, the clover just goes, look at all this sulfate, and away we go. And then over 6 or 7 months of the growing season in the New England, nothing's growing there now, it's way too cold. As you can see, superphosphate, we can get, what, nearly double the clover yield over putting in oily rag type rates of sulfur. And when we put our new product in, you can see that there's only 1/3 the amount of sulfate. So the clover doesn't jump away at all. But over time, as more and more of that sulfur is released, as the microbes oxidise our elemental sulfur, we're getting increasing yield responses. We continued this on after Richard finished his honours. We kept on monitoring this for 3 or 4 years. And what we found was, yeah, we could still pick up the pastilles 3 or 4 years later, like literally, pick them up. But this continued to be the highest yielding product. And that's a big difference. That's a lot of money in the bank for a grazier. The surprising thing though is what's going on with this superphosphate, because it's actually pretty good. It's not as bad as you would think. 800 mil rainfall, these were wet years. I've got 5 minutes. Wow. Okay, let's slow right down and heaps, no, okay. So what's really interesting about this superphosphate treatment is somehow we haven't lost our sulfur from the system as quickly as we thought. Normally we would spread this and then the rain would move through that coarse sandy topsoil and take our sulfur away, and it'll hit a really disturbing hostile B horizon. If you don't know how bad Australia's soils are, I can tell you exactly how bad they are. It hits that B horizon, it runs down the creek, and we lose the sulfur from the system. But we're actually doing pretty well. We keep on getting a bit of sulfur. Now, how is that happening? Why haven't we gone lots of sulfur and then shoom, vanished? What's happening is the plants here have taken up our really available jelly bean type sulfate, and then they've been grazed, and grazing usually removes about half the sulfur from the system. Cows munch it, and then they, I don't know if you saw the picture, then they urinate and they defecate back on the paddock, and so roughly half the sulfur is cycled through organic sources. And then they trample on their food, and so they bury some of that. So what we've done is we've taken our sulfate and we've converted it into an organic source of sulfur. And remember, the organic source of sulfur has that same mechanism. You still need microorganisms to eat the organic matter to release the sulfate for the plant. So we've essentially, with the superphosphate, which is lucky because we've been adding it for 80 years, we've actually captured it into biomass and then started a slow cycle. No, it eventually runs down. The cycle eventually, as it mineralises, and if there's not an active root system to take up that sulfur, then we lose it. It will leach out. Winter rainfall is desperately bad because the plants are brown and frosted and not active and rather cold, much like us. And so any sulfate that's free in the soil gets washed away. But if we've got it protected in an elemental form, as elemental sulfur, the rate that that's oxidising, that's determined by the temperature in the soil as well. And so it's not really oxidising over winter. As things warm up, so it will start to oxidise. And so it's a perfect little buffer and capacitor for storing sulfur in our system. And so now we find that many products are available in the market that incorporate aspects of pure elemental sulfur into them. And it's not just because elemental sulfur is cheap. It's cheap for two reasons. One is it's a waste product, but it's also cheap because when we add fertiliser, it's the purest source of sulfur on the planet. It's 99% S. When you're adding superphosphate, it's 8% S and a whole pile of calcium and phosphorus and oxygen that you have to carry around. That all weighs something. So elemental sulfur is the perfect input. It's cheap, it's incredibly efficient, and it's the most efficient fertiliser you can possibly add. But you do need microorganisms to oxidise it, release it, break it down. So I'm going to wrap up there. I believe that I'm handing over to Mahdokht online. I just leave you with a picture there of some sulfur, elemental sulfur oozing out of a volcano. There are places in the world that send people down into active volcanoes to mine elemental sulfur. We're not using any of that in our experiments. We're using other sources of elemental sulfur. Thanks, Nanda. Do you want me to sit down? No, Drew's going to take charge.
All right. Let's thank Chris for that talk. And so it was really amazing to hear about the work you're doing there, Chris, and your colleagues. And I think quite importantly, how important something as simple as elemental sulfur can be, and even just the form at which it comes is quite important for the food that we hopefully eat, and the efficiency for all of our farming. And I think the ability to Well, as you rightly put out, to control the way we put that sulfur back into our system, and the way it gets used by the plants is quite important. It probably gives us a little bit of a hint as to how important sulfur might be in a range of other areas of society. And so with that, I'd like to take the opportunity to introduce tonight's second speaker, Dr Mahdokht Shaibani. So Mahdokht is a lecturer at RMIT University. She is an energy storage researcher, inventor and analyst, and has a PhD in mechanical engineering from Monash University. Joining us from the lands of the Wurundjeri people of the Kulin Nations, please welcome Mahdokht.
Thank you for the introduction, Drew. Good evening, all. It's a privilege to be here as a speaker alongside Chris. And thank you, Chris, for the truly interesting talk and setting the grounding for me somehow. I would like to acknowledge Wurundjeri people of the Kulin Nation as the traditional owners of the land on which RMIT University stands. My name is Mahdokht Shaibani, and I'm a lecturer at the Department of Chemical Engineering at RMIT University. I'm also a battery engineer, which hardly makes me sound like an expert at any event, even at the dinner table. Sometimes I feel like half the people that I talk to are basically more up to date than me when it comes to the advancements in the battery world, which is why, in addition to frequent review of the scientific literature, I kind of have to have a quick glance at the news every now and then to basically keep myself in the know. So before talking about my research, I would like to basically remind us how our perspective of lithium-ion batteries has changed throughout the years, how lithium-ion batteries have become a lot more than the biggest trend in technology. I believe you all remember our time of low battery anxiety, the overwhelming fear that our smartphone battery dies and we will be literally dysfunctional. Thanks to longer lasting batteries of our smartphones today, we kind of don't have that anxiety anymore. Let's take the example of iPhone 11, which was introduced 5 years after iPhone 6. And its battery lasts twice as long. But does that mean that the energy storage capability of lithium-ion battery has improved by a factor of 2 over a period of 5 years? Well, looking at this table, we realize that iPhone 11 lasts longer because it uses a battery that is literally twice heavier than what it was in iPhone 6. So no, in fact, the rate of increase in the energy storage capability of lithium-ion battery has been quite incremental, almost plateauing. You know, the same old chemistry of decades ago is still there. Range anxiety, basically the fear that our EV battery does not have sufficient charge to take us to the destination. I believe you all agree with me that we kind of don't have this particular type of battery-related anxiety in Australia because we don't drive EVs in Australia. There are not many of them to purchase. They are expensive to purchase, and the very limited number of charging stations across the country could do a lot more than an anxiety to the EV driver. Should we drive EVs? I'm not going to argue with that. But anyways, in those parts of the world that they drive EVs, this range anxiety is actually the main driving force for the car makers to continue investing relentlessly in new battery chemistries, new electrodes that could improve the energy storage capability of batteries. Energy bill anxiety, a definite thing in Australia. And a common solution for us to fight it is the use of residential solar panels. In fact, while we don't drive EVs in Australia, we kind of rank first in the world for the residential uptake of solar panels. And lithium-ion batteries, as wonderful as they're actually a source of anxiety here for us because they're expensive. We cannot simply afford to have them coupled with our rooftop solar panels to use the energy of renewables while the sun is not shining, which is like, you know, the endless winter in Melbourne. And to address this particular type of anxiety, we are always looking forward to cheaper lithium-ion batteries. We kind of don't care as much about the storage capability of these batteries. Climate anxiety. Well, Australians are no strangers to the consequences of the climate issues, bushfires, floods, and so on. And they are becoming increasingly more common, which means that whatever it is that we are trying to do to mitigate these issues, it's not working. And you know, climate anxiety, while a negative state of feeling, it's actually beneficiary because it prompts us to act. In fact, the lack of climate anxiety in some of the decision makers in this country, I'd say that's what is concerning. But how is this that batteries could contribute to climate anxiety? Aren't they supposed to be our most powerful tool in fighting climate change? Well, an increasing number of people are raising some serious question marks around the environmental and social costs of making lithium-ion batteries. What is the carbon footprint of making the batteries? What are the associated health risks for those miners who mine for the battery minerals in developing countries such as Congo? And you know, probably a big question for all of you, is this true that the EV that we drive is as green as the electricity that is used to charge the EV battery? Well, RMIT researchers, they made this online interactive tool and tried to incorporate all the emissions involved in making and driving of several cars. The gray area here represents traditional cars. The pinkish reddish area represents the hybrid cars, and the yellowish area represents the battery-driven car. The figure on the left, it clearly shows that making EVs is currently very emissions intensive because of the battery. But the figure on the right, that takes into account everything, the cycle life of the car, if you like, it clearly shows that the much greener choice to drive is actually EVs. So while we should definitely be concerned about all the aspects of making the batteries, that should never stop us from moving towards electrification. Solutions to address these anxieties? Well, thankfully, there are many practical solutions out there, from innovative and responsible mining to recycling and reuse of the used batteries. But one game changer solution is to invest in entirely new battery chemistries, batteries that are potentially greener and better than lithium-ion batteries. And one such a chemistry is a lithium-sulfur battery, which is my expertise, and it relies on the devil's gold, elemental sulfur. There are a number of battery chemistries that promise to store more energy than lithium-ion, as you could see on this figure on the left. And lithium-sulfur kind of shines here. It, on theory, it could store up to 6 times more energy than lithium-ion. In practice, 2 to 3 times, which is wonderful. We use this term specific energy in the battery language, which basically means that the higher the specific energy, the lighter the battery. So the future lithium-sulfur battery, which is potentially considerably lighter weight than lithium-ion battery, you would imagine not only it could be useful in several existing applications, but on account of being lighter weight, it could actually unlock a couple of new application avenues where the light matters, such as in aviation, drone delivery, for example. In addition to be potentially lighter weight, lithium sulfur also promises to be cheaper and more sustainable than lithium-ion batteries. As Chris mentioned, sulfur is dirt cheap, and you can find it at all the right places on the earth. And this is as opposed to the rare earth minerals, such as nickel and cobalt, that are used in lithium-ion batteries. As for the lithium, while it is considered as a critical mineral, there is no foreseen shortage of lithium. And Australia is actually responsible for producing more than 50% of the world's lithium, and we are a pretty reliable country. through this video, I quickly show you how lithium-sulfur battery works. So as the name suggests, the battery has two electrodes, a lithium metal as the negative electrode shown here by the blue color, and elemental sulfur as the positive electrode or the cathode, separated by a component named the separator, and a liquid electrolyte is used to carry lithium ions, represented here by blue spheres, between the two electrodes. During a discharge, lithium ions, they travel from the lithium metal anode to the sulfur cathode. They react with sulfur and they form this series of complex species that in our language, battery language, we call them lithium polysulfides. But from now on, I'm going to simply refer to them as sulfur compounds, Li2S, Li2S4, Li2S2, and eventually the final discharge product of the battery, Li2S. And then during the following recharge of the battery, lithium ions, they travel back to their original place, the lithium metal anode, and sulfur anions, they revert to being elemental sulfur again. So large capacity brings big problems. Lithium sulfur battery has a superior storage capability thanks to the formation of these sulfur compounds, but it also has a very limited cycle life, which is again due to the formation of these sulfur compounds. Two major issues that I will be discussing here are material expansion and material shuttle. When lithium reacts with sulfur, the size of these products, the sulfur compounds, are actually twice bigger than the initial sulfur, which means that the electrode will swell up. So I took this microscopy image of a fresh sulfur electrode before cycling. Then I put the electrode in a battery, cycled it for a while, disassembled the battery, took the electrode out, and did some more imaging. And the image on the bottom left is the result. You could see that the electrode has lost its integrity. You could see colonies of isolated particles here and there, which means that the electrical wiring of the electrode has been lost. And that results in rapid capacity fading of the battery. The other big problem, material shuttle. These sulfur compounds, these yellowish sulfur compounds, they're highly soluble in the battery electrolyte. They continuously leach out from the composition of the electrode, from the structure of the electrode, and they get dissolved in the liquid electrolyte of the battery, which means that cycle by cycle, we lose a bit of our electrode material. And it's not only that, they also travel through the separator, they reach to the other electrode, the lithium metal electrode, which happens to be highly reactive, and they cause all sorts of problems there as well. Again, I took these photos of lithium sulfur batteries in a coin cell type configuration, and you could see that the white color of the separator, which is the reservoir for the battery electrolyte, has turned into yellow, which is due to the presence of these sulfur compounds that have leached from the structure of the cathode. So I'm an engineer with a limited knowledge of chemistry, so I often try to borrow ideas from other disciplines to address the issues of my batteries. As Chris mentioned, the sulfur compounds, they are negatively charged. So I thought, what if we apply this thin coating of a material which is also negatively charged on the sulfur electrode? Then if the sulfur compounds are generated, this thin coating, this barrier coating, should be able to repel the sulfur compounds back to the electrode. So I used to work during my PhD studies in a water purification laboratory where they made these membranes to basically purify water from unwanted cations. And a material that was successful was graphene oxide, a negatively charged material. So what I simply did was that I borrowed some graphene oxide ink. I printed it on the sulfur electrode, which lasts no more than a few seconds, and you could see the thin coating on this microscopic image on the right. And the improvement in the result was outstanding, as you could see in this cycling figure on the bottom. But we always knew that we needed to do a lot better than 400, 500 cycles to rival lithium-ion battery in terms of capacity, retention, and cycle life. So we thought if we could immobilize the sulfur compounds right within the electrode, just stop them from leaching out, that would be the most efficient strategy. So we started our research through the sulfur literature, wherever that sulfur was applied, agriculture, cosmetics, food, and so on. And our brilliant PhD student, Yingyi Huang, she came across this dusty geochemistry paper that showed glucose could actually form these strong organosulfur bonds with the sulfur compounds of the very same nature that we use in our batteries. And it can help soil retain the sulfur compounds. That was a big clue for us. So we did our own simulation, and it was confirmed to us that sulfur could actually react with glucose to form strong bonds. We also did some straightforward experimental evaluation. For example, we made a battery electrolyte, and we dissolved these sulfur compounds in it, which gave it this yellowish color, as you could see on the image on the left. And then we added some glucose powder to the solution. We left it overnight, and we noted that the yellowish color is actually fading away, which demonstrated that glucose has been successfully able to absorb the sulfur compound from the electrolyte. Quantitative analysis of the powder of the electrolyte further confirmed this observation. And the rest was pretty much straightforward for us. We systematically added controlled amount of glucose to the composition of the electrode, and we monitored the performance of the battery. And at the end, we noted that we only needed a few % of glucose in our recipe to improve the cycle life of the battery by 1,000 cycles, which is a record in the literature of lithium-sulfur battery. We also did some imaging of the sulfur electrode, and we noted that glucose is actually doing a lot more than that. As you could see in those images, instead of forming a dense microstructure with basically no room for the particles to expand, to breathe, glucose helped with formation of this open 3D, some sort of a web-like structure with a lot of room for expansion of the particles, which was another contributing factor to the improvement in the battery cycle life. We were obviously encouraged to make large-size batteries and test our batteries in a weight-crucial application. And I guess the video is not working here, but we tested it. We tested the batteries in a drone, and it was quite successful actually. And I'm not going to go through the reasons, but making large-size batteries is actually such a big challenge in a university laboratory. But we do it pretty much every day in our lab, thanks to a dedicated team of engineering students and staff, and we continuously improve the energy performance of our lithium-sulfur batteries. In this table, I summarized the pros and cons of lithium-sulfur battery and the potential applications of this chemistry. I'm not going to go through it, but just to give you a quick idea, the more green colors and also the darker the green color, the better. And you could see here that the future lithium-sulfur battery and even the current lithium-sulfur battery, they could potentially address many of our battery-related anxieties. I would like to acknowledge our wonderful PhD student, Yingyi Huang, and also my wonderful colleagues, Professor Mahdokht Shaibani and Professor Matthew Hill of Monash University. Thank you for having me today, and I'm happy to take questions.
Thank you, Mahdokht. What a wonderful time we have had. To paraphrase Sherlock Holmes, it's all elemental sulfur. So as you can see, the link between the two, the soil chemistry, battery chemistry, all linked by sulfur. And what an amazing change. I mean, one is adding sugar, one is adding sulfur, but it's all to yield the crop and yield the time of the battery and make our life less anxious. So I would like to invite questions from the audience for both our speakers. Please submit your questions by scanning the QR code on your screen if you are watching online, or by coming up to the microphone on here in the auditorium. So we will start where, who is winning? This is a competition, online versus people here. Well, remember, people on the left can do online too. Okay, sorry.
There's no one there, so the people online are winning. So.
It's invisible people. So, oh, there are questions here, sorry. So Drew, you start?
Yes. So to begin, a question for Mahdokht, actually. Just in reference to the lithium-sulfur batteries, can you make a comment about whether they would be less likely to combust in, say, a road crash than the current lithium technologies?
That's a very good question. Yes, lithium-sulfur battery is inherently safer than lithium-ion battery, and that's one big reason for actually the car makers to look into using it in big electric vehicles, such as in buses and e-trucks and so on. And the reason is that the positive electrode, sulfur, it does not have any oxide-based compounds as opposed to the ones that are used in lithium-ion battery. And yeah, at an event of an accident, they're the main source of basically the explosion, the reaction that causes the explosion.
Okay, you carry on, Drew. There'll be,
All right.
No, we will win. We have one person here coming up. Thank you.
A question for Mahdokht. What is the automobile industry's response to the lithium-sulfur battery? Are they interested in quite a new technology, or are they too wedded to existing production methods that they are not really interested in investing in such new technology?
Oh, that's a very smart question. Unfortunately, the big car makers, such as Tesla, they are extremely attached to the good old lithium-ion batteries, and it makes sense with all those gigafactories out there. The battery should be extremely convincing so that they would be happy to invest in an entirely new battery chemistries. So at the moment, it's mainly startups, no big manufacturer.
Thank you. Drew?
Yes,
and then we will have someone from the floor. So you go. Yeah.
Fantastic, thank you. This is a question for Chris. So in your talk, you mentioned about the role that bacterium play in the oxidation of sulfur. Can you comment on whether there's any plans that you're aware of to introduce bacterium into the sulfur-containing fertilizers to kickstart that oxidation over time?
No, there's no plans that I'm aware of to introduce. They keep on changing the name of the bacteria. It used to be thiobacillus, now it's thiooxidans, because they thought, well, thio is sulfur and oxidans is oxidized, so okay. They call it thiooxidans. No, what happens is those organisms are all present in the soil pretty much everywhere naturally. And so what happens is when you give them elemental sulfur to chew on, their numbers multiply up. Bacteria multiply quite quickly, and so the release rate of elemental sulfur is it's sometimes constrained. Like you do have a lag if there aren't naturally that many bacteria there, but there's always one or two, and so they do multiply up when they've got that competitive advantage. You've just given them their type of jelly bean, so they will breed and take over the world. I'm curious with Mahdokht putting glucose into her
Yeah.
sulfur batteries, how is she going to stop the bacteria from eating the glucose? Like, in soil, glucose goes.
She will stay away from the thioxylus, whatever the bacteria is. But it's funny that everyone wants sugar or jelly beans. We will have a question from the floor.
Questions to Chris. Thanks very much for your talk. We know that by increasing sulfur, you got an increase in plant harvest. But increasing sulfur onto the soil also decreases the pH. So to what extent is the increase in growth due to the decrease in pH and not the increase in take-up of the sulfur?
Yep, okay. You must, I think you secretly know something about sulfur oxidation and the generation of sulfuric acid. So yes, the thiobacillus will chew on the elemental sulfur and convert it to sulfuric acid, which will lower the pH. The rates that we apply, though, are only in the order of 10 kilos per hectare. And so I remember having a debate. I play golf. I love golf. And the greens at Armidale clearly had evidence of sulfur deficiency through them. And I said, look, why don't you put some elemental sulfur out, because greens are made of sand and you need a steady supply of sulfur to stop my greens from going patchy. But the Greenkeeper's Bible clearly states that you can't use elemental sulfur because it will burn, acid burn, the leaves. And it didn't matter how many times I told him that there's actually enough buffer capacity in soil to soak up those additions of acid from the sulfuric acid from just oxidizing 10 kilos of sulfur, that it's just not going to burn. And I said, look, the 8th green is enormous. Give me a quarter of it and we'll put elemental sulfur out, and I guarantee you we won't be burning the green. And no, Greenkeeper's Bible is, you can't forswear the Greenkeeper's Bible. You're right, it does generate acid, but at the rates that we apply it's not high enough. It's buffered by the negative charge in the soil. Yeah.
Drew?
This is a question here for Mahdokht. So you mentioned in your talk about the introduction of nanomaterials such as graphene oxide. We've got a specific question here that's talking about some new materials coming on the scene, and in particular, can you make comment of the role of boron nitride nanotubes in the development of the lithium-sulfur batteries?
There are a large variety of nanomaterials that have been used in lithium-sulfur battery, all with the idea to basically immobilize the sulfur compounds. And yes, boron nitride is one of them. Thanks to the nitrogen groups of boron nitride, they could actually improve not only the immobilization of the sulfur compounds, but also the kinetics of the battery, which is an inherently slow battery. So yeah, it's one of the successful ones. But in terms of the real world application, lithium-sulfur battery is supposed to be an extremely cheap battery because it relies on the extremely cheap sulfur. So the addition of any additive that doesn't make much sense cost-wise, such as, for example, this particular material, I would say it will make the idea of a cheap replacement for lithium-ion battery a bit questionable.
Okay, we'll have a question from the floor.
Thanks both. They've been fun talks. I'll target it to Chris just because I'm a plant guy. So you talked about the benefits in multi-seasons of the cows basically pooping and then allowing a remobilization through the bacteria again in a cycle. What's going to happen if you did the same strategy to crops, perennial and annual crops? Would you have you wouldn't get that benefit of recycling, or would you get that if you left the stubble there at the end type logic?
Yeah, so the way cropping agriculture generally works in Australia now is that stubble is retained. We're very concerned about carbon and keeping carbon in the system. And there is sulfur and carbon stored in roots. It's roughly 50-50 between roots and shoots. But we are harvesting and exporting a significant proportion of sulfur out in both grazing systems and cropping systems. So the cycle should be the same. It's probably a little bit slower for a cropping system because annual crops anyway, you normally grow them through to grain and they senesce and the carbon concentrates up as everything gets put into the grain, and then we take the sulfur and the nitrogen away and we're left with high C to N ratio material and higher C to S ratio material. And so it's going to release sulfur, but it's going to release it more slowly. Whereas in pastures, they're normally constantly growing and they're normally constantly there, except in Armidale in winter. Does that answer your question? Yeah.
Thank you. Drew?
Yeah, a question here for Mahdokht. So the question comes from a bit more of the engineering side and the manufacturing. Is there much of a difference for manufacturing the lithium-sulfur electrodes compared to how they're manufactured today?
It's a wonderful question. Yes, there is actually a big difference, and probably one of the biggest challenges ahead of the future manufacturers of the battery. And the reason is that in lithium-sulfur battery, as opposed to a lithium-ion battery, we actually use lithium metal. So you may or may not know that in lithium-ion batteries, we don't use lithium metal. We use lithium in a form of a compound, which is safe to like handle and process and everything. Whereas lithium metal, it's highly reactive and it requires a specialized environment. Like at the university laboratory, we use an argon environment. So yeah, handling and processing of the lithium will be one of the biggest challenges ahead of the manufacturer of this battery.
Okay. Drew, you carry on. I see a bank of questions over there, so.
Yeah. All right. So this is a question for Chris, and in particular, your clover study. So, and I think this is a question that's on most people's minds, but did you find many four-leaf clovers in your study? And with the addition of sulfur, do you see an increase in the percentage of four-leaf clovers?
We might be the lucky country.
That's a very, very useful question. I do like that, the lucky country. But no, well, we actually generate lots of leaves because we grazed it with a lawnmower. And so we essentially shredded all of those 3 leaves into 4 leaves and 5 leaves and 8 leaves. And yeah, no, we don't see an increase in the percentage of 4-leaf clover when we add sulfur. It's not like Jack and the Beanstalk magic. So, yeah.
You carry on, Drew. Okay.
Yeah, well,
please do come up from the floor if you have any questions. Yeah, Drew.
Well, this is another question for Chris, and to those people online, I'm now merging 2 similar questions together. But there's been some questions here about Australian native plants, and generally speaking, their low requirement for essential macronutrients. And do you have any comments about how our native plants seek out sulfur and their needs for sulfur?
Okay, yeah. Yeah, I could talk forever about about plant requirements. Yeah, it's an interesting idea that Australian natives have lower requirements for these macronutrients. Usually that is just the mother of necessity because there's just not that much in Australian soils. They are so old and weathered and leached, so they just have to make do. The moment you fertilise these plants, they go crazy. So essentially their growth is constrained by lack of macronutrients. And they are adapted, and Australia has heaps of species that are adapted to essentially strip mine soil for phosphorus. In terms of sulfur requirements, there are a number of species that have quite low critical concentrations of sulfur, less than like the classification for a macronutrient in a plant is roughly anything more than about 0.1%. And you can actually grow and there are native species that have such low requirements. The problem from an agricultural point of view is that when you lower the tissue sulfur concentration down to 0.1%, there's not enough sulfur for the animal. So, you actually have to shandy up your pasture and supplement with sulfur almost sometimes directly to the animal to overcome sulfur deficiency if you're trying to find the most efficient species in the system. They will grow and generate biomass, but the cattle won't. So maybe kangaroos are fine. I haven't done any research on kangaroo sulfur.
There you go, another research grant coming
No,
up.
kangaroos are, no. I've got enough of them on my place. So.
We have two questions from the floor. So I think we might, after that, we end there. Yeah? Yes, okay.
Thank you very much. I really enjoyed the talk on soils, but my question's to Mahdokht about charging infrastructure for changing chemistries. Can the charging infrastructure that's all being developed and rolled out now cope with new battery chemistries?
Well, lithium-ion battery and lithium-sulfur battery, they are extremely different in terms of the electrode materials, the processing, and everything. So, and I've got to say that lithium-sulfur battery or any other battery chemistries that scientists or industries are currently exploring them, none of them are supposed to entirely replace lithium-ion battery. Lithium-ion battery is going to be there. It's wonderful. We all agree on that. So these sort of new battery chemistries, they're simply supposed to lessen the burden of the rare earth metals that are used in lithium-ion batteries. And some of them, like lithium-sulfur, thanks to the potentially lighter weight properties of the battery, they could unlock new applications. But I would say that lithium-ion battery is going to be there, so the infrastructure is going to be there. If industries are interested in new battery chemistries, there needs to be additional infrastructures to make them.
Okay. Last question.
Thanks again. My questions to Mahdokht. You indicate there was a good supply of lithium in the world, and certainly it's not in immediate danger of undersupply. But according to the Royal Society, there's only a 10% recycling rate for lithium, which is pretty poor, doesn't augur well for the future. So what comment would you have on recycling of lithium and other precious metals?
Yeah, that's a good question. That's actually very true. So as opposed to lead acid batteries, that the recycling rate of them is nearly 100%. We currently recycle no more than 5–10% of the used lithium-ion batteries. But the thing is that, as I mentioned in my talk, there is no more than 2–3% of lithium in a lithium-ion battery. So even if you go through the full recycling of all the used batteries, I would say that the cost of recycling is probably going to be more than simply mining for the lithium. And yeah, there is no foreseen shortage of the lithium deposits. So probably recycling of the used lithium-ion battery for the purpose of recovering the lithium, there's probably no economical incentives for that. So the sort of, I think I would like to add that recycling lithium-ion battery could be worthwhile for recovering of the precious rare earth metals, such as nickel and cobalt. For example, we use 15% cobalt in like the big batteries that are used in EVs. So yeah, those are basically, they make sense to recycle those minerals.
Okay. I think we'll have to stop our discussions, even though I can see that discussion could have continued. So thank you all for your great questions, great participation from the audience here and the online audience. But as all good things have to come to an end, we have to close this evening. Big thank you to both Chris and Mahdokht for joining us tonight, and my co-convener, Drew. It's always a pleasure, Drew, to work with you. We also thank Jira at GS Station Wines and the Shine Dome team for refreshments earlier this evening for those who are able to join us in person. Thank you for to all of you for joining us tonight, and we hope to see you again for the next installment of Surprising Science on 11th October, titled The Life of Lightning. Thank you and good night. Thank you, Mahdokht.
Thank you.